Hello everyone, and welcome to the first of a series of videos that I'm preparing to help you go through these chapters, the main chapters of the book that will be the topics that you will be evaluated in the final exam. We'll discuss the proper format for the exam in a different moment, okay? So the series of videos will focus mainly on chapters 2, 3, and 5. So these are the main chapters that you need to study a little bit more in detail. But then I will present a brief summary of chapters 7 and 8. Towards the end as well, I will try to present you a little bit a brief description of some topics in chapters 4 and 6. But these two will not be topic of the exam. But from chapter 2, for example, you can use a little bit of that knowledge to finish your the practical part of your assignment. Okay, I will also guide you towards the assignment. So mainly, the exam will be then based on the first assignment that you have delivered, and a little bit more that will come from the second one. But we will discuss that when the time is right. Okay. So for this unit step here, the unit step then is defined as a sequence. So you have to look at this as a sequence of samples, just that in this case most samples are equal to 0 except 1. And this one sample will be located if you look at the argument of this function here. So when this argument is 0, that is where you will find this non-zero sample. Okay, for example, here we're defining that this delta, this impulse unit sample here will be 1 at n is equals to 0. Okay, and 0 elsewhere. Here we see that we can also displace this impulse. It can be located anywhere. So here we then apply a delay or advance in time depending on the value of nd. So nd can be actually, I will write it down here, and nd can be is an integer, can be positive or 0 or negative. So it's an integer. Okay, so when you look at this argument here, to find the place where you will find this non-zero sample, just make n equals to nd. Okay, so for the unit step here it's a little bit different, that instead of one sample we have a sequence of samples, and here we know where it starts. Here it says it will be 1, a sequence of ones, in this case that starts at 0, and it moves to the right to plus infinity. So for positive values of n or 0 we will have 1, and 0 for negative values in this definition here. As before, we can also apply delays here or advance in time, so we can displace it to the left or to the right if we want to. So in any case, any value that we choose for nd, okay, we will find the starting point by making n equal to nd. If I give you an example here, if I have a signal example for this one here, I have a signal then that I will call x of n here, and I'm defining it as u of n minus 2, for example. Okay, so this is then a sequence that is starting at n equals nd, and in this case is 2. So it will start at 2 and move to the right with values equal to 1. Okay, and 0 elsewhere. So this is our delayed unit step. Okay, so if this value here is negative, then it means that we are displacing to the left. That you can try. So those are examples of basic signals that we need to know about. And now I'll talk a little bit about basic systems. This you can find at section 2 of your textbook. So discrete time systems. So now we talk about the transformation that you will apply to an input to get an output y of n. Input x of n to get an output y of n. So t is defined here as a transformation. Later on we will define it in a better way, okay, through the convolution and things that we have gone through, but I want to summarize everything for you so that you can have a quick reference for this. So let's see an example. This is an example of a system that, by the way, is very it's one that will pop up quite often also in our analysis. So here we are defining a system that just applies a delay to the input. So the output is obtained just by applying a certain delay nd to the input. Actually, here we define it in a more general way. We are saying say that nd, then it's a positive value. Okay, it's greater than 0. It's a positive value. More specifically, I could say that nd belongs to the positive integers, and n in general can be any signal, and n can be can assume any value from minus infinity to infinity. So n is also an integer. So now let me give an example here. Suppose we are defining, say, let x of n be defined as a complex exponential, defined like this, okay? And then to find the output y of n will be given by our input signal, but delayed by nd. All right, I can rewrite this a little bit and split it into a product. I could say that then the output will be equal to e to the j let's say minus j omega nd, because I put this negative sign here, times e to the j omega n. And here we note a very interesting thing is that when we use this complex exponential as an input, we could then factor it into two parts here, where I can see clearly here that this was my original input, and this part here, we will analyze it later on, is called it's the frequency response of the system. Okay, we will discuss this later on. And we can also see here the interesting fact is that when we have any input of this form here, it's a complex exponential, when it goes through this class of systems that we will be discussing, like that they must be linear and time invariant, the output then is a version of our original input signal that you can see here, but which is scaled by a factor here. See, it turns out that this factor in this case is a the absolute value is 1, but it applies, so this is the analysis in the time domain, so we see the delay here that will correspond to a change or in the angle, because as we have seen before, the exponent here corresponds to an angle, because this is if you remember well, this is a cosine of this angle here minus j sine of this. So this is an angle, and we see then this is the angle can be also called a phase. So we see there that's a phase shift. Okay, so we will come back to this, and towards the end I will give you an example where you can apply this. So this, summarizing what we have seen so far, we have discussed a little bit about different signals, and we have talked about systems, how we are describing the systems, and how we can calculate the output of a system. Okay, now the next the next part is where we talked a little bit about properties of discrete time systems, and these properties, as these 5 properties that I keep talking to you, and they are popping up all the time. So I will divide them here. These 2 here that you see, linearity and time invariance, these are very fundamental to this class of systems that we will be discussing. And also we see that most of our systems will have memory, so they will not be memoryless. Okay, and these 2 final properties here, causality and stability, are also very important. And if you remember well, this stability is can be directly related to the Fourier transform, and then we extend the analysis of the Fourier transform to the Z transform. This is a topic for chapter 3, where we could then analyze both causality and stability at once. So here we should also remember that the Fourier transform then will be regarded as a particular case of the Z transform. Okay. All right. Now, still in chapter 2, now we restrict our analysis to linear and time invariant systems. Okay, and then we talked about the convolution that is represented here by the star, the asterisk here. And we also saw that the convolution is actually commutative, so I can say that I'm convolving h of n with x of n, or x of n with h of n. It's the same. If I write down the equations, then they become like this. And by the way, we are introducing now here the concept of impulse response of the system. So now we have then 2 entities here, the output, the input, and the impulse response. The impulse response, just take it literally, is the output that the system will provide you if the input signal is just one impulse. Remember, if you go back a little bit, you will see the when we talk about systems. So an impulse like this, if you provide this kind of input to the system, it will give you a response or an output that we just call the impulse response, because it's the response of the system when the input is an impulse. Okay, yeah. So now we have defined this convolution here, and if you remember, I advise you to go a little bit again through section 3 in chapter 2, where you analyze the convolution, and we came up to this definition here. Here we see that we are also expressing this idea of commutativity, that this can be written in either ways, and they are both valid. Okay, we will come back to this again. I'm just laying out the things that you have to focus, and then we will start using this in exercises and applications. Then in section 2.4, we talk about properties of linear and time invariant systems, which then will lead you to this basic figures here. I just well, we are not dealing with complex systems like this right now, so we are looking at one system at a time, so you will not need this at the moment, but in case you, so this then it's section 2.4 with property of linear time invariant. This you can just read a little bit through it if you just to remember, because we have covered this part in the course already. Okay, now another topic that we will develop more carefully in chapter 3 is this linear constant coefficient difference equations. This will be in many of the exercises that we will be talking about. So I'm just mentioning it here, but then we will detail it on when we address chapter 3. Also, this frequency domain representation of discrete time systems and discrete time signals and systems here is where we then start analyzing the Fourier transform, okay, where we introduce the Fourier transform. And here we are introducing a very important concept that I mentioned a little bit before. You can go back in the video and see the example when we consider this complex exponential as the input to our system. Okay, so this eigenvalue property of complex exponentials for discrete time systems is a very interesting property, because as we saw in the basic example when we talked about the ideal delay system previously, when we have a signal like this as input to the system, we will see that the output of the system will be a scaled version or a delayed version, because it will be actually scaled by a complex value. So, and this complex value, as we have seen in the classes, when you multiply anything by a complex number, there are two things that you can achieve. One is that you can scale the value in terms of absolute value, or you can apply a rotation to it. This rotation is the delay. So you can do these two things: scale, which will be like amplify or attenuate, or apply a time shift, okay, a delay. So these are the two things that we can do here. Now, if I use this as a input to the system, and I remember the definition of the convolution here, I will use this one I will use this one here, this version here, because so that will tell me the following: the output of the system will then be y of n, just applying the definition of the convolution, will be a sum from k varying from minus infinity to infinity of h of k e to the j omega, but as before, as you can see here, so I'm using this version here, h of k. Now the input is, instead of having n, I will have n minus k. Okay, so my input here was e to the j omega n. I will replace n by n minus k. Okay, now if I do as I did before for the, when I had the example of the ideal delay, You see here what we did. So we will do the same thing that we did before for the ideal delay. We'll try to factor this because this is a multiplication that we have here. We'll split it into two factors. We'll do the same. So if I apply the same idea here, then I will have a sum, k varying from minus infinity to infinity of h of k. Now I will move this k here, e to the minus j omega. Okay, this minus came here, and then I put the other part here. So I had s before, so this is the input. This is the input, and this one here will be a factor that actually it's called, since we're talking about this is an eigenfunction. You see, this is when we have an eigenfunction as input, then the output is given like this, where we have the eigenfunction which is scaled by a factor, and this factor that is scaling the eigenfunction, we call it the eigenvalue. Well, don't let these terms bother you that much. You will get used to them anyway at a certain point. But this, if we look at this, sometimes it's written so it's a function of omega, e to the j omega. See, now the impulse response is written as a function of e to the j omega, and I will represent it like this. Okay, and this usually is called the Fourier transform. The Fourier transform. Then I will define it as the only in this case I will replace k by n, but it's the same. I'm just changing the variable, still the same, just to make it look I mean, it's more common to write it as a function as using n instead of k, but it doesn't really matter how you write it down. So here we go. This is the Fourier transform. Okay, so I will go through this very quickly now, just to tell you the following. When we have inputs of this kind, which are called complex exponential, actually we can have a more general form for this. Okay, I could have generalized that to the following. I could have an input like this: x of n is equal to z to the n. Okay, so this is similar, just that now z is equal to r e to the j omega. So so let's I could write like more generally. We could have this case. Okay, so this is also a complex exponential, and they are eigenfunctions for linear and time invariant systems. So what we have here? So when your input is a function like this, and you're given this system function like this, the Fourier transform of the system impulse response, then you can easily calculate the output just by multiplying instead of calculating the convolution, because you know that if you plug it in the convolution you'll get this. So we'll use, when you have exercises that give you an input like a complex exponential, which can be like this, where r is equal to 1, but more generally r can be anything, then you can just multiply by the in this case we say multiply by the Fourier transform. When you have a case like this, multiply by the Fourier transform, as you can see here. So this is the input that we see here. But in more general case, you can have inputs like this, where you could multiply by the Z transform instead. We have seen the Z transform, which is just an extension of the Fourier transform. Then I will just write it down here, because since we have gone through it, it's easy for you to remember that it's an extension of the Fourier transform. And now, instead of being a function just of e to the j omega, it's a function of z that we have defined before. Okay, we have defined like this. It will be like very similar. And z to the minus n here. So this is the z transform that we'll see in details when I describe the main topics for you, the main topics from chapter 3. Okay, so we're almost half an hour into this. This is basically what you need to know about chapter 2. But there's something very important here, some exercise that I recommend you to do, which are a continuation of these results that we are obtaining here, is to calculate the Fourier transform for many different cases, which will generate actually in some theorems here that I ask you to try to prove, right? See, for this one here, for example, I need the Fourier transform of it, right? I just write the formula for the Fourier transform that we have just seen here. And so this is the formula for the Fourier. Any given signal can be the impulse response that I see here, but it can be the input, which we called here x of n. It can be the output, which we called y of n, anything, okay? So what will happen is that when you're calculating either the Fourier transform or the Z transform, you just replace here by the signal that you're given. The rest will be the same, okay? So all these theorems that I'm talking about now, actually you can apply the same for the Z transform later on. I really encourage you, when you finish this, try to go through these exercises, and you will see you can pause the video here and try to repeat these examples by yourself. You can do them at the end of chapter 2, but also you have some similar at the end of chapter 3, where you, instead of applying the Fourier transform, you're applying the Z transform, okay? Right, so when I just plug in the signal of interest here, then I realize what I need to do is to have it in a way that it resembles the Fourier transform. So I'm talking about this Fourier transform. What I need to have is this. See, when you have a negative sign here, then you can write h of e to the j omega. So this is a function then of j omega. Pay attention to the fact that when you have a negative sign here, you say that it's a function of e to the j. This is the convention, function of e to the j omega. Okay, so now for this exercise here, you see, I have this negative sign. So before I had a positive sign I had a positive sign here. So I will try to have something very similar, and so I will just have to remove this sign from here, which means that I will have to put it up here. What happened here is that there was a change of variable, but you don't have to do this, okay? But here just for change of variable from n to l, but you could just have changed the sign, say n and plus n, because you're changing the signs, okay? If you change here, you have to change that as well. So what happens is that when I look, then compared to the original, this is okay because it's positive, but here it should be negative, so that I can say I have a function of e to j omega. And because in this example it will appear with a plus sign, as you can see here, Then instead of saying that it's a function of e to the j omega, I will say that it's a function of minus e to the j omega, because the sign must be the opposite, see? And for theorem 5, so this was for number 4, 5, I will let you go through this, but this is related to the fact that when you find the derivative of an exponential, it's very easy, because you just the derivative is the derivative of the exponent, and the function appears again. So if I had the derivative here, then I would have n, but I also would have j, minus j, but I don't have minus j. So that means that if I would integrate, if I integrate this, then this would go back, right? You could say that. If I integrate that, then of course the n would disappear, but I didn't have a j here. Then I would have to divide by j, minus 1 divided by j here. And then we have this case of when the signal is n x of n. You have another theorem here for this case here, when you have a sequence multiplied by a complex exponential. Again, you plug it in the Fourier transform formula, and you analyze a little bit, you put them together. You see that now what you have, instead of a function of e to the j omega, we have now a function of the whole thing here, see? So it's pretty straightforward. It can give you some not hard time, but some time to go through this. But if you have some spare time, I really encourage you, because it will help you be more comfortable with calculating the Fourier transform. This is another case that we saw before, right? And we're saying here that if you have a delayed version of your input, instead of x of n, you have x of n minus nd, then the result will be this. And this is an important conclusion, and you'll have it summarized. You have all of them summarized in the table. So again, we plug it in here, and we have to make a change of variable. We would say that in this case we are replacing n minus nd by L, which means that if L is equal to n minus nd, you write it in the form of an equation like this. We're saying that you're replacing n minus nd by L. L is equal to n minus nd. That means that n then will be equal to L plus nd. That's why we wrote it down here. And that you have here is equal to L plus nd. And then you just, because you have L here, you just factor it again to have this match for L, and then you have this factor here that then you have, this is then the Fourier transform of x of L that we write here, which will be a function of j omega. We see clear j omega there, but then you have this factor which will then lead you to this result here. So I recommend you to play a little bit around with this. We have now come to the almost to the end of this section here, but I would like to finish with an exercise. Okay, it's a long 30 something minutes. Let's go through an exercise here, and this exercise is I'll tell you, it's 214, exercise 214. Give me a second here. So we come to the textbook, go through exercise 214. Problem 214. Here it is. Okay, so try to find it in your book. Actually, what we will apply do here is using this concept of eigenfunctions. Okay, so this is an exercise that you have to use that concept. That's why I think it's appropriate here. First, I will you see, it says it becomes difficult for you to read, you please check your own textbook. Okay, so here's the problem. So here we are have this relationship input and output. We see if this eigenfunction property applies here. It says a single input output relationship is given for each of the following three systems. So for system A, we have x of n. We see it's an exponential. Now the question is it a complex exponential? This can be a little bit tricky, but it's actually a complex exponential. I will guide you through the details. So when you look at the input and look at the output, we see the relationship. We see if we have this idea of scaled version of the input. See, I have you're given an input. See if the output is a scaled version of the input. That means you'll see the input clearly multiplied by a factor. Can be a complex number or a real number in this case. And your options are the following. If you identify this exercise in your textbook, it will be easy for you to read. But it says, based on this information, pick the strongest possible conclusion that you can make about each system from the following list of statements. So we have these statements. The first one says the system cannot possibly be linear and time invariant. The second one says the system must be linear and time invariant. So in this case, you'd be very sure that it's linear and time invariant. Okay. Remember that this idea of scaled version of the input output relationship, as we can see here, is a conclusion, is a consequence of the convolution, which emerge from the assumption of linearity and time invariance. So these things are related. And the two last possible choices are these. And this one says the system can be linear and time invariant, and there is only one linear and time invariant system that satisfies the input-output relationship constraint. Sorry, the system can be linear and time invariant, but cannot be uniquely determined by from the information in this input-output constraint. Okay. Now I will put the book aside and keep your book in front of you so that you can follow what we're talking about here. So see if you can identify exactly this problem here that in my book is 214, but in yours might have a different number. Just check check it, please. Put it aside and then we will resolve it. Okay. So now the first case is system A. So this is problem 214. I will not write the title there to save some time. System A. Says the input is 1/3 to the power of n, and the output would be then 2 times this input. Well, before we